Okay, thank you. All right, so today we're going to talk a little bit more about sort of this issue of what I described to you last time, getting started on this concept of collocation. So if you remember in the Euler method, and the reason I keep going back to the Euler method is not because I love the Euler method. I really don't like the Euler method. But the thing is that these methods get complicated. So if I'm writing down pages and pages and pages of math, it's so complicated that you lose the message. I don't want to lose the message, all right? So because of that, I'm trying to keep the scheme initially simple so you can see what's going on. If you remember, we had this kind of a system where we had approximated the derivative with a finite difference approximation, and we set it equal to the right-hand side. And if there's control, then we added control. Actually, you know what? Let's just add the control, because I think this gets confusing if you don't add control into this. So UK and TK. And this was for k going from 1 up to k minus 1. Right? Now, if you look at the scheme, what you see here is this is where the concept of collocation comes in, all right? These equations, if you remember, I told you, when you do this with collocation, you're not time marching. You're not solving for the value at the kth step and then solving for the value at the k plus first step, given the values at the kth step. You're writing the whole system of equations down at once, and you've got this entire system, which forms a vector system of equations that is being solved, and then you're minimizing this cost function, which is an approximation to the cost. Let's start with this right here. What is this right here? This, which is the left-hand side. So this is the left-hand side. And it's an approximation to dx dt evaluated at tk. That's what this is, right? This right here, if I take this part, this is the right-hand side. And it's the function that describes the dynamics of the system. So look at what you're doing. If you look at this just in its really basic terms, you're saying that I'm going to approximate the derivative at some point, in this case tk, and I'm going to set that derivative at that point where I'm doing this approximation to the value of the right-hand side or the dynamics at that point. So what you've got here is, since these two things are being set equal to each other, right, this is what's called collocation. Why is it called collocation? It's because I'm putting two things in the same place, right? This is being evaluated or being approximated at time tk. This is the value of the right-hand side at time tk. So therefore, I'm putting two things which are different from one another, both evaluated at the same point in time. I'm setting them equal to each other. So I'm collocating. The way this actually gets written is you don't write it this way, because when you actually solve nonlinear programming problems, you write it in this form. You write it as xk plus 1 minus xk, well, this is one way to write it anyway, divided by h, minus fk, where I'm abbreviating now, this is equal to, say, fk, equals 0 for k going from 1 to k minus 1. Now, generally, we don't write it with the h in the denominator, but that's just a scale factor. So this becomes xk plus 1 minus xk minus h times fk is equal to 0. If I really want to be strict about this, let's put a k on everything. All right? So that becomes an algebraic equation, right? That is clearly an algebraic equation. It's not a differential equation anymore, right? So what you've done is you've transcribed this the original dynamics, because you remember the original dynamics are x dot equals f of x, u, and t, right? I've transcribed this system into an algebraic problem. So this is no longer a differential problem. It's not a continuous problem anymore. It's a discrete problem, all right? So this is algebraic. All right. Now you can see, like, let's think about what I just did. All right, in more general terms now, not just with regard to Euler methods. What it says is that if somehow I can do a derivative approximation at a bunch of points, and I could set that derivative approximation equal to the value of the right-hand side of the dynamics at also a bunch of points, then I could do this for any range there are a whole range of ways I could do this, right? And there are an infinite number of ways I could do this. This is just one way to do it, right? So what we generally do when we do collocation is we think of it this way. We take the time interval. We're doing the same thing. We take the time interval. We've got this time interval from t0 to tf. We break it up into these things which we call mesh intervals. Some people call them segments. Doesn't really matter what you call them. Now, this is t0, t1, t2, all the way up to tf, which is t sub k. All right, so it's t sub k minus 1. So what we want to do is, we want to say, well, I know that the solution to my problem, say it's the state x of t, is some function of time, right? But I don't know what that function of time is ahead, right? So what you do is you say, well, I know that the actual solution looks like something. I don't care what it looks like. It just looks like something, right? What I'm going to do, though, is I don't know what this function is. I have no idea what this function is, right? If I knew what the function was, I'd be done, right? Because then I'd have the solution, right? So what you do is you say, well, over each of these intervals, what I'm going to do is I'm going to approximate the state with some polynomial, or some function, which I'll talk about polynomials in a minute. And I'm going to do that over each segment of the problem. And I'm drawing this kind of in a hokey way on purpose, all right? Which is that this is the, let's just take this one right here. This is the approximation of the state in mesh interval k, where this goes from t k minus 1 to t sub k. Now, if I'm approximating the state, I could approximate the state a whole bunch of different ways, right? So I could say that the state is going to be approximated by another function, all right? So this is not the same function, right? This is the actual state. This is my approximation to the actual state, right? And I'm going to say that's equal to some combination from j equals, say, 0 up to m of c sub j times psi sub j of t. But of course, these c sub j's depend upon whichever mesh interval I'm in, right? So this is actually going to be the state approximation in mesh interval k, right? And then these also can depend upon the mesh interval if you really want to be technical about it. So then you say, well, all right, so I've got this. Now what can I do with it? Well, I can do what I did over there, right? I can differentiate it. So you could say x dot k of t is then going to be approximated by this function x dot k of t, which is going to be the sum from j equals 0 up to m of c sub j k psi sub j dot k of t. Well, that only tells you part of the story, right? Because that tells you now I have this function, which I've approximated by this other function. And now I'm going to say, well, I can differentiate that function. I can get this approximation to the derivative. But if you look at that, now you say, well, OK, now I can. That gives me information about the right-hand side. Now the question becomes, how do I then do the approximation so that I enforce it at the right number of points? So let's just suppose, for example, suppose that psi j k of t are polynomials that span up to power, say we got power here, right, of m minus 1, right? Because if I start with 0, right, 0 is constant, 1 is first degree, 2 is second degree. So if I go up here and I put a 1 in here, I've got a linear function, and that's a polynomial of degree 1, so this is actually a polynomial of degree m. Okay? So now I've got a polynomial of degree m. And you ask yourself the question, let's go back to real basic stuff here. How many coefficients do I need to know in order to be able to determine a polynomial of degree m? What's that? Polynomial of degree m. M plus 1, right? Quadratic needs 3 points, right? Cubic needs 4 points, right? In order to uniquely determine the polynomial, I need one more coefficient than the degree of the polynomial, right? So you need m plus 1 coefficients, right? So how many equations, if I'm going to do this right, how many equations do I need to enforce in each mesh interval in order to be able to properly be able to approximate the function in that mesh interval? If I have a polynomial of degree m, right, its derivative is a polynomial of degree what? M minus 1, right? Anytime you differentiate a polynomial of degree m, you get a polynomial of degree m minus 1. So it's always 1 degree lower. How many coefficients are uniquely needed, are needed in order to be able to determine a polynomial of degree m minus 1? M, right? And we're going back to basics here, right? So if I do this from j equals 0 up to m here, right, I got a bit of a problem, because if I do this, how many coefficients do I have? What's right? This need m plus 1 coefficients to uniquely determine. I should finish this thought. A polynomial of degree m. But we're, like I said, we're actually collocating not on the function, we're collocating on the function derivative, right? So if I purely collocate on the derivative, right, that's not going to be enough information, is it? I mean, or I'm going to over-collocate the problem, right? So I can't just collocate on the derivative unless I do it, you know, correctly. So what we do is, we say, all right, if I differentiate this, I get a polynomial of degree m minus 1, which is uniquely determined from m coefficients. But I have m plus 1 coefficients. So I need one more condition in order to be able to do this, right? I can't just collocate on the polynomial, right? Because if I collocate on the polynomial, I'm going to have, on the derivative of that polynomial, I'm collocating on a polynomial of degree m minus 1, right? Which requires m coefficients. But how many coefficients do I have in that approximation? I have m plus 1, right? So I'm off by 1, right? Because I need m coefficients are what will uniquely determine that polynomial. So what you do is we actually add a condition. We say that, all right, we're going to collocate on the polynomial at a bunch of points in the interval, right? And then what we're also going to do is we also have to collocate on the function value. So what we do is we choose points on each mesh interval, tk minus 1 to tk, and we call these points, let's call them tau 1 up to tau sub m, okay, to collocate x dot k of t, all right? So those are the m points that I'm choosing in here. So I've got a bunch of points in here that I'm choosing. And now you need something else, though, in order to be able to do this. You need one other thing. You're out of options as far as the derivative goes, right? Because the derivative is a polynomial of degree m minus 1. If I collocate that at m points, right? How am I going to do that? Well, if you look at this, you say, all right, well, if I do, how many coefficients do I have? I have m plus 1, right? So I can't just collocate on the derivative, because if I purely collocate on the derivative, what kind of system do I have in each segment? I have an overdetermined system, right? Because I have one more coefficient than I have equation, right? So I don't have the right number of equations and unknowns, right? So in addition, what we do, I'm going to put this in quotes, collocate, we're not really collocating, on the value of the function at some time point in tk minus 1 to tk. Now, when I start, if you think of this as a time marching, and I'm starting here, what's the value of the function that I know? I know the value of the function at the initial point, right? So what you can do is you could say, well, xk of tk is going to equal what? It's going to equal, let's start at the first point. Let's start at t0. So x0 of t0 is going to equal what? It's going to equal my known value. Remember, suppose I start with a known value of the initial state, right? So if I start with a known value of the initial state, I'm going to say the function in the first segment, or the first mesh interval, is going to equal the known value. Now I have the right number of conditions, don't I, right? Because this right here is equal to what? This is equal to the sum from j equals 0 up to m of that thing, cj0, and then I've got psi dot j of t0, right? There's a k in here. Right, if I plug in the value t0, I can say my function approximation is going to equal this value at the initial point, right? Now, that gives me the value at the first segment. Now I say, okay, I'll move over to the second segment. What has to be true about this state as I move across the segments? So at these points right here, what has to be true about the state? It's not true about the control, but it's true about the state. Yeah, the state has to be continuous, right? So the state has to be continuous, must be continuous at each mesh point. So that means that the value of the state approximation in segment K at the final point has to equal, let's call this tk minus, has to equal the value of the state approximation in at the beginning of the next mesh interval. Well, let's take this off. Right? So now what you see is, you see that if I'm at an intermediate mesh interval, here, I say that the value of the function that I'm using in the approximation in the kth mesh interval, at the end of this mesh interval, has to match the value at the beginning of the next mesh interval. So every time I add an interval, I'm adding another function condition to the problem, right? If I only had one interval, I have one function value that I'm evaluating here. If I add to a second interval, I say, okay, I'm now going to collocate the polynomial, which is a polynomial of degree m minus 1 at m points, right, in the interval. And I'm going to say that whatever the value was that I got from the end of the first interval, it has to match the value at the beginning of the second interval. So that gives me yet another condition on the function value, right? So every time I do this, I add a condition on the function value. And I get the right number of conditions every single time, right? Because I have m plus 1 coefficients in each mesh interval, and I'm collocating on a polynomial of degree m minus 1, which gives me m, but I need one more coefficient, so that gets collocated by enforcing the condition on the state. This is what's called, in collocation, this is what's called the continuity condition. It's also called a checkpoint constraint. I don't know why it gets that name. A checkpoint constraint. I don't know where the term checkpoint constraint comes from, but that's the word that gets used. Now, believe it or not, you may find this really hard to believe, but when you do Euler forward, you're doing this. It doesn't look like you're doing this, does it? But think about it. When I'm doing Euler forward, what assumptions have I made in the process of doing this? I made an assumption. First of all, how many points am I using in the collocation? I've got these mesh intervals, right? I'm integrating from T0 to T1, T1 to T2, T2 to T3, right? So when I get to T1, how many points have I used to do this, to collocate the derivative? I've used 1, right? I'm only collocating at point tk. That's what we said, right? So if I'm collocating on the derivative at 1 point, using this logic right here, what was the degree of the polynomial in the approximation that I needed to start with? right? So let's go through this argument right here. So if I'm collocating at m points, right? So I mean this is a polynomial of degree m minus 1, right? I'm collocating at m points. So I'm collocating at 1 point, which means that had to be a polynomial of degree what? It had to be a polynomial. It had to be a constant, right? I'm collocating as if it were a constant, right? So what I'm doing is I'm saying that the value of the function is going to, but what I've done is I've made it so that the solution at the point k plus 1, at the end of that mesh interval, it has to match the value that I get at the beginning of the next mesh interval. So wherever I stop and start, I wind up with continuity. So what did that mean that the original function had to be? It had to be a polynomial of degree what? 1, right? Which means it was a straight line, which means I was collocating using a piecewise straight line. My function is a straight line. The derivative is a polynomial of degree 0, which requires one coefficient to uniquely specify it, right? So I've got the right number, right? Because I've got one condition on the derivative. And what else do I have in these problems? I have an initial condition, right? The initial condition is x at t0 is equal to x0. So I've supplied the missing condition to be able to count for the second coefficient, right? Because if I'm doing a straight line requires 2 points, right? I'm collocating at 1 point for the derivative, which is correct, because the derivative is a polynomial of degree 0, which requires 1 point. But I have 2 coefficients, so I need to account for the second coefficient. The second coefficient gets accounted for by the boundary condition, right? And then as I add another segment, I say that the value of the state at the end of that mesh interval has to equal the value of the state at the beginning of the next mesh interval. So let's go through this in a little bit more detail. So let's do this for Euler forward. For Euler forward, what we do is we say this. We say the state in mesh interval k gets approximated, so this is x k of t, gets approximated by this, which is going to equal C0k plus C1k times t. All right? If I differentiate that, what do I get? I get C1k, right? It's the derivative of that, right? It's really simple. So now what I say is I say C1k, right, which is my derivative approximation, is going to equal f of, well, I've got to stick in x k of t and u k and t k. Well, u k is my approximation of the control. So you see what I've done here is that's the function that goes in here that gets used to evaluate this, right? And then this over here is my constant that I'm solving for, which is the derivative. This problem right here is the same as the problem that I have over there. It doesn't look like the same problem, but it's the same problem that I have over here. It's just that I've rearranged it in such a way that now what I'm doing is I'm solving for the polynomial instead of doing a finite difference. So you get this, but you also get the condition that you've got x at t0, sorry, capital X, 0 at t0 is equal to x0, and x at tk at the end of segment k has to equal x k plus 1 at that same point. So what you get here is that this Euler method, which I explained to you as collocation because of the way collocation is defined, can be rewritten simply by using a polynomial as the approximation and then going through the math in the same way. You wind up going through the math, you differentiate, you set the polynomial equal to the value of the right-hand side of the dynamics at each of the points, and you just step through each of those points. And of course, you don't have to use a straight line, right? I can use a quadratic, I can use a cubic, but every time I do that, I now have to break the segment into more and more intervals inside, right? So I have to break this up. These are what are called stages. So what I would do is I would say, well, for all of these, every time I increase the degree of the polynomial in the approximation, I add another stage to the problem. So I have another point that I'm doing this at. So of course the question becomes, how do you actually decide how you choose these stages? So this is like the age-old question in quadrature. So now what we're going to get into is we're getting into quadrature approximations. So imagine that you have a function, and you want to be able to approximate the integral of that function, because that's what we're doing here. We're integrating functions, right? So we want to approximate the integral of the function. So I'm just going to look at one interval, because if you get into multiple intervals, this gets really confusing. So just imagine I have one interval. And just for simplicity, I'm going to make this even easier, right? I've got a function, f of tau. And I'm going to put tau on the interval -1 to +1, because it really doesn't matter what interval I put it on. So -1 to +1 is as good as any, right? I can scale the interval any way I want. So I've got this function, and we want to approximate the integral from -1 to 1 of f of tau d tau. So basically, I want the area under this curve. All right, now the question is, how am I going to get the area under this curve? Well, you can choose a lot of different points, right? I can do this any one of a number of ways. I can choose evenly spaced points, and I can approximate by just doing rectangles. I can approximate by doing a straight line. I can approximate by doing a quadratic over each interval. I can keep increasing the degree of the polynomial, and in such a way that I wind up getting a better and better approximation to the integral. But what you really want to be able to do is you want to be able to do this approximation in the fewest number of points. Why do you want to do it in the fewest number of points? Well, you want to get the most accuracy you can without making the problem any bigger than you need to, right? So if I do it with the fewest number of points, I make my computations easier, right? Because I'm doing less calculations in order to get this. So what we're going to talk about now is we're going to talk about n-point quadrature. This is a classic thing that comes up a lot, which is to approximate the integral of this function. So what you get when you do an n-point quadrature is you get this. I want to approximate this integral by this. Where I pick these points in such a way that these values out here are what are called weights. So these are quadrature weights. So what I'm going to do is I'm going to basically take the value at these points, tau 1, tau 2, tau 3, tau 4, up to tau n. I haven't told you where they are yet. Okay, so they could include -1 and 1. They may not include -1 and 1. It depends on the way you do the quadrature. All right. And what I do is I sample the function at each of these points, and I do a weighted sum. And the constraint is that the sum of the weights has to add up to 2. It basically has to add up to the width of this interval. All right? So what I'm going to do is I'm going to try to figure out, well, what is the best way to do this? So it turns out that if I did uniformly spaced points on -1, let's suppose I include -1 and 1 as points in that quadrature. So tau 1 is actually equal to -1, and tau n is actually equal to +1. So I include the endpoints. If you do this, what you get is you get a quadrature that if you pick the points to be evenly spaced, every time you increase by one more point, you only have increased the accuracy by whatever the amount is of the width of that point, the width of that point to the next point. So if you pick, so in other words, think of it this way. If I pick n points, if I double it to 2n by dividing all the intervals in half, right? I've only increased the accuracy by a factor of 2h, which is really not much, right? Or h over 2, because of the fact that I'm going to do some uniformly spaced approximation. So it turns out that the best way to do this, if you want to minimize the error, so then we get into this question right here, is let's suppose we ask this question. And I'm not going to go through all of this today because the rest of the lecture, we're going to go through some of this stuff in more detail. I'm not going to get to all of it today. Which is to suppose we want to choose tau 1 up to tau n, and W1 up to Wn such that we minimize the error in the quadrature approximation. So in other words, we want to minimize e, where e is equal to the integral from minus 1 to 1 of f of tau d tau minus this quadrature. So it turns out that, I'm not going to go through all the proofs because this is not a numerical methods course, so I can't go through every single one of these proofs. But it turns out that if you want to minimize this error in the L2 norm, so if you want to make, so basically the Euclidean norm, the minimum error is achieved as follows. I'll put it on the next slide. Next board over here, which is that we have three sets of points. First set of points is if I include both -1 and 1. So if tau 1 is equal to -1 and tau n is equal to +1, then the points we get are what are called the Legendre, Gauss, Lobato points. And what they are is they are the roots of the nth degree Legendre polynomial roots of the derivative, sorry, write that down. Roots of the derivative of the nth degree Legendre polynomial together with the points -1 and +1. Now, if you think about that just for a second, if it's the nth degree Legendre polynomial and I take its derivative, I get a polynomial of degree n minus 1. So the roots of an n minus 1th degree polynomial, how many roots do I have? If I take the together with -1 and +1. So you get n plus 1 total points when you're all done, right? So actually this should be, sorry, this is n minus 1th. Be careful here. It's n minus 1th degree Legendre polynomial, so I'm using n points. So if you take the n minus 1th degree Legendre polynomial, you differentiate it, you get a polynomial of degree n minus 2. A polynomial of degree n minus 2 has n minus 2 roots, right? But I have n points, right? I've got n quadrature points. So I need to supply the missing points. So you do that by supplying the points -1 and +1. So this is the first case. In the second case, if tau 1 is equal to -1 and tau n is strictly less than +1, so you don't constrain the last point to equal +1, then the result is what are called the Legendre Gauss Redau points. And what they are is they are the roots of this polynomial, which is p n of tau plus p n minus 1 of tau. You get those roots. Now, it turns out that if you use these points, you could equally well have used the points that are the symmetric points of these, which is that you could set tau n equal to 1 and then free tau 1, and you wind up getting the exact same result because I'm just constraining one point, not both endpoints. Those are the Legendre-Gauss-Redau points. The third set, which is that if neither endpoint is constrained, which means that when I say that, I say tau 1 is greater than 1, negative 1, and tau n is less than plus 1. Then what you get is you get what are called the Legendre-Gauss points. And these are the roots of the nth degree Legendre polynomial. Now, what's interesting about these points, a lot of stuff you can read about these points, but what's really interesting about them is they look like this. So if I just pick for every value of n, there's a set of these points. So if I pick a value of n, let's just say n equals 5. I'm going to do this for n equals 5. What I get for the LGL points is I've got a point at negative 1 and a point at plus 1. And then I get the symmetry that I get these 3 points in the middle. So this here is tau equals 0. This is tau equals 1. And this is tau equals negative 1. So you can see that the endpoints are included. So this is LGL. If I do LGR, what I get is I get a point here. And then I get this kind of weird sort of behavior that I get points that look like this. This is LGR. But you notice that there's no point at 1, because I said that if tau 1 is equal to negative 1, so tau 1 has to equal negative 1, and the last point has to be strictly less than plus 1. So it can't equal plus 1. All right? That's what you get. That's LGR. If you do Legendre-Gauss, you get something that looks a lot like Legendre-Gauss-Lobato, except for the fact that you wind up with this. And these points are not evenly spaced, by the way. So I'm not drawing them very well because I've only got 5 points. I don't want to clutter it with too many points. These points are not evenly spaced. So I don't have collocation here. I don't have anything over here either. So if you look at these sets of points, you say, well, I'm solving an optimal control problem, right? So clearly, every time I go across a mesh interval, right, I'm going from negative 1 to plus 1, I somehow need to account for the fact that I have a function value at plus 1, right? So it seems that when you look at this initially, you say, well, the LGL points look like the best set of points to use, because if I use the LGL, because by the way, I'll write one other property down about these points, which is what makes them interesting to use for quadrature. So, and then we'll talk about optimal control for a minute, and then we'll stop, which is that the key property of LGL, LGR, and LG points, which is that the LGL points exactly integrate a polynomial of degree 2n minus 3 using n points. So what that means is that if my function, which I'm trying to integrate, is a polynomial of degree 2n minus 3 or lower, if I use n points in that quadrature, I integrate that polynomial exactly. Now that's a pretty powerful statement if you think about it, because it says that if I had a polynomial, let's just stick in a number. Let's suppose I wanted to integrate a 10th degree polynomial. Then how many LGL points do I need in order to exactly integrate a 10th degree polynomial? It says that it will integrate a polynomial of degree 2n minus 3 using n points. So if 2n minus 3 is equal to 10, then that means what? n minus 3, or 2n is equal to 13, right? Which means I need between 6 and 7 points, right, to be able to integrate that polynomial exactly, right, using n points. So if this is equal to 10, 2n minus 3 is equal to 10, 2n is equal to 13, so n is equal to 6.5, but you can't have 6.5, right? A polynomial has an integer degree, right? So I need 7 points in order to exactly integrate a polynomial of degree 10, which means I need less points than the degree of the polynomial, right? I can use fewer points than the degree of the polynomial. That's pretty powerful, right? Because it's saying that in order to get an exact integration of this, I don't need as many points as the degree of the polynomial itself. So this is for LGL points. For LGR points, integrate or exactly integrate a polynomial of degree 2n minus 2 using n points. So that means that if I use LGR points instead of using LGL points, I get one more degree in the polynomial than for n points. I can integrate a polynomial one degree higher exactly than I can using LGL points. And by the last logic, the LG points exactly integrate a polynomial of degree 2n minus 1 using n points. So what I've done is so this is kind of weird, right? I mean, because what you've done is you're stepping from a situation where you've constrained both endpoints so that the quadrature points have to include both endpoints of the interval, to a situation where the quadrature points only have to include one endpoint of the interval, to one where they have to include neither endpoint of the interval. If you want to minimize that quadrature error, it turns out that in each of these three situations, every time you give up the constraint that you want to fix one of the endpoints, you gain a degree of accuracy in the polynomial approximation, which actually makes some sense if you think about it, because what it's saying is that I'm not constraining where those points have to lie. I'm letting them be wherever they want to be, right? In the case of LG, they can be anywhere on the interval. If it turned out that the solution was for them to be at the endpoints, it would have naturally just put them at the endpoints. But in order to minimize that error, you don't want any of the quadrature points to be at the ends. But of course now, I have this property that these three sets of points exactly integrate polynomials of degree 2n minus 3, 2n minus 2, and 2n minus 1. The question is, given the fact that they're so accurate, because they integrate polynomials that are much larger in degree than the number of points that I'm actually using in the approximation, the question becomes, how do you actually use these points? So this is actually the basis for these methods that I do a lot of research in my lab, which are pseudospectral methods. But they're not really pseudospectral methods. They're called pseudospectral methods. I really don't know why we ever got the terminology pseudospectral. It's bad terminology, but we're stuck with it. I guess we could change it, but then nobody would know what we're talking about, right? So what this really is this is really what's called orthogonal collocation. And the reason it's called orthogonal collocation is as follows, is that Legendre polynomials are a set of polynomials that are all orthogonal to one another. If I take the integral from -1 to 1 of any two Legendre polynomials, their inner product is 0, right? Because they're orthogonal to one another on the interval -1 to 1. That's the definition of Legendre polynomials. Is that, and the nice thing about Legendre polynomials is that because they're orthogonal to one another, you get this really nice way of generating one polynomial to the next polynomial if you generate the series of polynomials. But more importantly, when you look at the roots of these polynomials, they have this really nice structure to them, especially if you look at Legendre-Gauss or Legendre-Gauss-Lobato. They have this really nice structure to them, that they're symmetric about, the roots are symmetric about the origin, and they are, they're so that if you have an even number of points, they're going to be an even number of points below 0 and an even number of points above 0. If there's an odd number, one of them is always going to be at 0. The thing about these points is that when you look at them, they're orthogonal. You say, I'm going to collocate at these points. I haven't shown you how to do the collocation yet. I'm going to do that next lecture. You collocate at these points. And what happens is, in the process of doing the collocation, you get this really nice property that if you do it right, you get this very high accuracy in the approximations. Because remember, the goal of all this, what we're trying to do, is we're trying to integrate differential equations, right? We have an optimal control problem. What does an optimal control problem have in it? It's got a cost functional. It's got differential equations. In order to solve the differential equations, I need to integrate, right? In order to be able to integrate, I need to have some kind of integrator, right? I want to have a very high accuracy integrator because I don't want to use any more points than I need to. So if I can do this with a very high accuracy integrator, then I can gain a lot of accuracy for a very small or coarse approximation, which is what I want to do. There's another property to these points, which I don't have time to go into today because it's just going to get a little bit more, it's going to get a little longer than I want to, so I'll go over it next lecture, which is this thing of Runge phenomena. And that requires the next step in this process, which is how do I actually use these points together with a function approximation in order to be able to do the collocation. So what we're going to do next lecture, I still have a couple minutes, but what we're going to do next lecture is we're going to talk about how you couple using these points with the right kind of function approximation. So you can approximate the state in any mesh interval using the right functions in such a way that when you differentiate those approximations and then you do the collocation, you get this, you preserve the quadrature rule, which is the nice high accuracy quadrature rule that you get from using these sets of points. Well, at least in the case of Gauss and Radau, it's the three. Gauss and Radau. In the case of Lobato, actually, the whole thing breaks down, but I'll get into that next lecture. So what we're going to talk about next lecture is we're going to start talking about the fact that if you look at these points at a glance, it looks like Lobato would make the most sense because Lobato already includes the endpoints, and you need to have endpoints of the interval when you go from one mesh interval to the next. But it turns out that neither Lobato doesn't properly preserve the quadrature rule, and I'll show you next time that you can actually preserve the quadrature rules by using either of these two sets of points. And we'll discuss that next lecture. Okay? So this is going to take a while to develop all these methods. I'm going to spend one lecture at a time, and we're going to develop every single one of these methods. I'm going to spend one